Okay, good. Good. So now we go to our first topic in this course, and the topic is subspaces, not introduction anymore. Okay. So subspaces. This is going to be a long review of various aspects of linear algebra. Some of them might be familiar, some of them might be new. But what is important is also details. So please feel free to ask me to stop and explain anything where I go too fast and anything that is unclear. You can be sure that, you know, if you have questions, your colleagues also have questions. So just ask me whenever you feel like you need to stop. Okay. All right. Let's just go ahead. So first we begin with a review of least squares. Least squares is a probably familiar concept, right? Least squares. What is it? Find x that minimizes these relations. So ax minus y. Okay. So find such x that ax minus y by norm is as small as possible. So this value ax minus y is called residual. We would sometimes denote it as e, residual. So the difference between what ax is and what y is. Okay. If equation, let's say ax equal to y has an exact solution, if it has an exact solution, then you can make residual go to 0. Residual doesn't have to be bigger than 0, right? It can be 0 if the equation has a solution. All right, so E is a residual. If an equation doesn't have a solution, you would always have a residual. All right. Now this notation basically says that there's a second norm. What is the second norm? It is a square root of the dot product of the vector with itself. So you can say dot product of the vector with itself, square root. Notice that this is how you can write dot product. The vector transposed times the vector, that is the dot product. We call it inner product. All right, sometimes yeah. Dot product. Okay. So least squares problem can be called a problem of finding least residual solution. So solution that finds us the smallest residual possible in terms of the second norm. That is, by the way, where the name comes from. Least means least residual. Okay. The squares means second norm. That's fine. Okay, good. Let's solve it. This problem has an analytical solution, so let's find it. So the minimum of e squared. So the minimum of this norm, second norm, right, is achieved at the same time as the minimum of this function is achieved. Why? Well, because square root doesn't change where the minimum lies. So minimum of square root of x is the minimum of x. Okay. So the minimum, since we don't have, especially since we don't have any other constraints. So the global minimum of those functions, they don't have any other minimum, just the global one. It coincides for those two functions, right? Square root of x and x have minimum at the same exact place. All right, good. With that in mind, let us find extremum of this function. How do we find extremum? What is extremum? Extremum is a derivative of the function with respect to the variable that you want to optimize that is set to 0. You remember maybe from your calculus course that you could, for a function that looks like this, right? You can always say, where is the maximum? Well, it can be in a point where the derivative is 0. So for example, here, maybe here, right? But definitely not here, right? So we're not going to look for a maximum here because the derivative is not 0. But here and here, we can look for a maximum. Okay, good. Let us now look for the derivative of this function. We can find it, and we can set it to 0. Well, the derivative of this function is a product of two functions. So how do we find the derivative? We take derivative of the first, multiply it by the second, plus the second times the derivative of the first. But since they're symmetric, it's going to be, it's going to be just 2, right? Same as x squared. Derivative of 2x, same here. So that's, we get this 2 here. Now, a of x minus y, if you take, it's not just a function, it's also a nested function, right? What is the derivative of the nested function? You first take a derivative of the first, the outer function, right? So in this case, x minus y transpose ax minus y, you take derivative of those, you get 2 times ax minus y. You also need to multiply it by the derivative of the function itself. So ax minus y, derivative is a. So that's how a, transposed. So that's how you get a transposed. Right. Maybe this wasn't very clear. And if it is not very clear, what you can do is open the brackets here, take the derivatives, and see if you arrive here. There is a chance you will not arrive here because you will forget how to take a derivative of x transposed with respect to x. Right. And for that, it will be your first introduction to the amazingly complicated world of what I would like to call like tensors, but just linear operators where things are horizontal, vertical, etc. How to take a derivative of ax with respect to x transpose? How to take a derivative of x transpose with respect to x? Good questions. That is the problem on which you can test your skills. Right, but this is a correct solution, I promise you. Never take those promises seriously, but this is the correct solution. Let's open the brackets. We can get rid of 2 here. This 2 doesn't do us anything, so we get rid of it. And we have ax transpose a transpose ax equals to a transpose y. Clear how we got it right. This guy appeared here and here after we open the brackets. The rest is, I think, clear now. Okay, now the next step is to multiply both sides by a inverse. So we invert this guy and we get the expression downstairs. We get this expression. Why can we invert this guy? Good question. Maybe we can't. But if you're going to do least squares this way, you assume that you can. That is an assumption. If you cannot, then it is like, cannot be done this way, essentially. You have to do it some other way, right? But we assume that we can. By the way, can you tell me if this would work for tall matrices or for wide matrices? Someone tell me. Would this in general be invertible, this guy, for tall matrices or for wide matrices? Someone tell me. Just make a guess if this sounds too difficult to compute in your head. Tall matrices or wide matrices. Tall matrix is this shape. This shape is a tall matrix. This shape is a wide matrix.
I think A transpose multiplied by A is a square matrix.
Yeah, it is a square matrix.
Yes. So we can invert it.
You can invert square matrices only if their determinant is not equal to 0. So
yes.
Only if they are full rank. You sure it will always be full rank? Good question, right? Will it always be full rank? Will it always be full rank? The size of A by A of this matrix would always be equal to the size of X. So yeah, that is just one thing. Now, of course, if you look at this shape, you can say, I think, reasonably well, that if A is a tall matrix, or sorry, a wide matrix like this, right? Wide matrix, you cannot expect this to be full rank. It would have more, would have linearly dependent columns, and when you transpose it, would have linearly dependent rows. You multiply it, you would get a very big matrix with a rank, with a smaller rank. So basically, if Y has more elements than X, if X has more elements than Y, then what you would have is a rank deficient matrix here, and it would be difficult to invert it. That is just kind of like very loose arguments. The real arguments, of course, would be like, how many dependent columns does A have if the number of independent columns equals to the size of X? I think that's kind of just how you're going to discuss it in the real life. But I just want to draw your attention to the fact that this guy, its size is X, basically the same as X, okay? And if X is a, small as opposed to the size of Y, you would have a small matrix here. It will likely be full rank, okay? If Y has less elements than X, then it would be a big matrix here, would likely be rank deficient. And that has, you can make implications about data analysis, as in you would prefer to have less unknowns than measurements. This is number of measurements, number of unknowns. You want to have less unknowns than measurements. Otherwise, least squares doesn't make any sense. That is data analysis side of this problem. Okay. Now, if you are not convinced with my treating the discussion of the rank of this matrix, this offhand way, where I'm saying, oh, if it is wide, then it will be full rank, or not full rank. If it is tall, it would be good. You should be not convinced about that. By the end of the lecture, we'll be able to hopefully give you good instruments how to answer those questions. Okay. All right, but for now, we'll keep going. Okay, so this is called pseudoinverse. This is called pseudoinverse. We denote it this way by using a plus sign on top of a matrix. Sometimes people denote it with a cross or with a dagger. In the fancy publications that they literally draw a dagger. The same thing. Dagger, cross, the plus sign. Sometimes you see maybe even some other notations, but Yeah, those are typical. Those are typical ones. Okay, so it's called inverse. We sometimes call it Moore-Penrose pseudoinverse to mention people who worked on it. So yeah, I think pseudoinverse is a typical way to talk about it. There are other types of pseudoinverse. That's why we mention specifically which one we mean. Okay. Any questions about this software? Have you seen Pseudoinverse before? Have anyone seen Pseudoinverse before?
Yes.
Mm-hmm. So this is not the first time you encounter. Okay. Now let us see what we can do with it. So first, least residual solution to this equation is now written this way, right? So we want to solve equation on top. We solve it this way. That's it. That's it. In code, we would write something like x equals to pinf of a times y. So that's how we solve equations if we want least residual solution. We will prove later that this is also smallest norm solution, okay? Not just least residual, but also smallest norm. What do I mean by smallest norm? It means that this x would also be the smallest x by size, by how big its norm is, out of every x that provides you least residual. Okay, but we'll discuss it later. But yeah, this is what happens. You have, if you have many possible x which provide you with least residual, this one is going to be the smallest one out of all of them. Okay. Now, let us consider this issue. First, before we even move on, let us just look what happens if M is orthonormal. Do you remember what orthonormal means? Or examples of orthonormal matrices that you encountered before?
Rotation matrix.
Yeah, rotation matrices are orthonormal, indeed. Yeah, so orthonormal, I think often we say orthonormal matrix is the one for which its derivative is, its transpose is its inverse. Or I think a better way is to just say this is more or less a definition of orthonormality. So matrix times itself is identity. Of course, transpose here, because that's how you multiply something by itself, by transposing. You can say it more fancily as dot product of the columns of the matrix with itself gives us identity. Okay, good. That is what means to be orthonormal. So if it is orthonormal, then pseudoinverse is simplified because this guy here is just identity. So pseudoinverse is equal to M transposed, same as inverse. Right? Very useful, very useful. So if you want to solve least squares with the orthonormal matrix, you solve it this way. You don't need any pseudoinverses, you just transpose. Any questions? Okay, right. Now, let us try to find the residual. So it would be interesting to understand what residual did we get by solving, finding least square solution, right? Maybe zero, maybe not, right? So let us find the residual. So given this equation, least square solution is inf a times y. So pseudo-inverse a times y. Let us compute the residual. The residual is a times solution, right? Minus y. Well, that is the residual, right? We can we can do the following. We can take this expression for the least square solution and substitute it directly into here. Okay. And that is how we get this expression here. Right? I think it's clear enough, right? We have this is the original expression, and we substituted this guy here from here. Okay. Okay. So this is the residual. Now, what did we find? What we found is that the residual can be expressed in this way. A pseudo-inverse minus I is identity, times y. Okay. We don't need to memorize it. But what I wanted to ask you is to remember the structure. Matrix times pseudo-inverse of a matrix, maybe minus identity, right? Because we will see it again and again and again. It's not a coincidence, this structure. Okay. Now, we also understand now that AX, the closest it can get to Y is this value. Okay. That is as close as it can get to Y. So AX, maybe it can achieve Y. If it can achieve Y, then this will be 0, and hence this will be equal to this. Okay. If it can achieve 0. If it cannot achieve 0, then this will be as close as it can possibly get to this value. Why? Because we are solving least residual problem. Least residual, meaning that this guy is as small as possible. Right? And we showed that this is a solution that does. Okay, so this is as close as y as a times x can get to y. Interesting. Later we'll see that this guy is a projection of y onto the column space of A. Later, not now. But what I want you to see is that we have this just from a list squares. We have those A pseudo-inverse, A pseudo-inverse minus I. Those things come out of using list squares and computing residuals. Okay, just remember it. It will be useful later when we see those things. They will start to pop out. Now I can pop out somewhere. Okay. Questions for this slide? Don't hesitate to ask questions. I will be happy to expound. Okay, I'll move on for now. Now we are starting the core of this lecture, fundamental subspaces. So there are 4 of them: null space, row space, column space, left null space. Each matrix has all 4. You maybe have studied this in your linear algebra course, very likely. So some of it will be review, but I think some of it will be new. I'll ask you at the end of the lecture how much of it was new. We need to understand how those things work. That is very important. They are extremely useful. Those things are extremely useful. For example, the trick that I showed you at the end of the introduction, where I computed something 200 times faster, that was just using subspaces. All right, let's try to understand. Consider this problem. Find all solutions to this equation, ax equal to 0. Homogeneous linear equation. This is, high school, very familiar. Find all solutions to the system of equations. I can reformulate the same thing as follows. Find all elements of the null space of A. Find all elements of the null space of A. That is the same task. Find all elements of the null space of A. So, null space of A is a set of all vectors x that A maps to 0. So it is a set of all x such that ax equal to 0. That's it. That is what null space is. Though denoted as n of A, often it is denoted as kernel of A, or like this. We call it sometimes kernel of the linear operator is popular. So did any of you study null spaces in your previous courses? Any of you heard of null? No, I mean like studied null space in linear algebra?
Yes.
Okay, did any of you not studied null spaces in linear algebra? Is there at least someone who haven't studied it? Cool, I can assume that all of you studied null space. Good. It's very good. We are planning to go fast. I hope that means we can go fast. All right, how do you find null space? Well, we can generate orthonormal bases in the null space of A. In MATLAB, the function that does it is called null. In Python or SciPy, it is called null space. Okay. So the way you do it is something like this: A equal to null of A, or N equal to SciPy null space of A. Okay. So that's how you find orthonormal bases in the null space. Okay. So let's be clear what we find here. We find orthonormal bases. Okay. Next. So let n be orthonormal bases in the null space of the matrix A. Then, if vector x lies in the null space of A, it can be represented as can be represented as x equals to nz. X equals to nz. That is how a vector can be represented if it lies in the null space, where z are coordinates of x in the basis n. Okay. Okay. You can prove it, of course. I will leave it to you to think about it. Well, somewhere in this lecture we'll have examples of how to prove those kind of things. But if you're curious, just try to prove it. Your knowledge is definitely sufficient to do it. Okay, good. Now, we can find vectors which are not lying in the null space of A. Right? Of course, right? Not every vector is in the null space. We can even find vectors for which the closest element to them in the null space is a zero vector. What do you mean by closest? Well, it means the distance from x to this other vector, so their difference is the smallest, right? In terms of two norm, in terms of second norm. Let me give you examples. So we have matrix A looking like this. its null space is given by this basis n. The basis n contains one vector, 1, 0. So this this basis represents all. It spans all possible vectors, the whole linear space of vectors that A puts to 0. Okay, makes sense, right? You multiply A by n, you 1 times 0, 0 times 1 gives you 0, 1 times 0, 0 times 0 gives you 0. Okay, good. Now let us see concrete examples. So for example, this guy minus 2, 0, it is the same as minus 2 times n. Or this example, 10, 0, this is the same as 10 n. Both of those are in the null space. Okay, fair enough. This vector 1, 1 is not in the null space. Why can I say it is not in the null space? Well, clearly you cannot multiply this by anything to get 1 here. So it cannot be in the null space. And even simpler even, multiply this x times a, you get 0 times 1 plus 1 plus 1 times 1 is 1. So already not 0. So not in the null space. The closest vector to it in the null space is this vector. You can trust me, or you can try to prove it, or whatever. How did I compute it? Well, I knew that this guy is a problem. This can be anything. So in this case, I set this to 0, and this is what I got. You can prove that it is the closest element by saying, okay, if I increase this guy a little bit, it would still be in the null space, so nothing will change, but it will be further away from this vector. Okay. If I decrease it a little bit, it will be again further away from this vector. Why? Because the distance between them is 1 minus 1 squared plus 1 minus 0 squared, that in square root. That is the distance. So if you change this, the square root will increase. If you modify this in any way, you'll go out of the null space. So you cannot modify it. All right. So that is how you can prove that it is the closest element. For this vector, by the way, the closest element to it in the null space is 0, 0. You cannot find anything closer to this vector in the null space. Because if you increase this, the distance increases. If you decrease it, the distance increases. So that's it. So notice we have this phenomena where a vector is not only not in the null space, the closest element to it in the null space is 0. Okay. It's just an illustration of what happens. Now let us see why we needed to know this. All right. Any two vectors, x and y, whose dot product is 0, are said to be orthogonal to each other. Okay, so two vectors, dot product is 0, so they are kind of like this, right? They are orthogonal to each other. So let me write it some. So for example, this vector and this vector would be orthogonal to each other. Their dot product is 0. Okay. Another definition: vector y whose dot product with x, with any x, where x lies in the linear space L. Okay. So vector y whose dot product with any x in L is orthogonal. The dot product is 0. So sorry, we lost part of the definition here. Let's see. Is equal to 0. So whose dot product is equal to 0 with any x in L is said to be orthogonal to the subspace L. Okay. So if your vector y is not only has 0 dot product with x, but it has 0 dot product with any x from some subspace, we can say it is orthogonal to the whole subspace. For example, imagine if this picture is 3D. Let me try to show you example. I will clear some space here and let me try to draw. So let's say you have this vector and you have horizontal plane, something like this, horizontal plane. Okay, so any vector on this plane, would be orthogonal to the pink vector, right? All those vectors on the plane are orthogonal to pink vector. So the pink vector, you can say it is orthogonal to the whole plane, the whole horizontal plane. That is an example. Right. Now, equivalently, you can say that vector y, for which the closest vector to it from a linear subspace L is a zero vector, such vector is called orthogonal to the subspace L. We can see the proof in the appendix A. Okay. But you can see now this idea, right? If you have a vector who is for whom the closest element in the null space is zero vector, that vector is orthogonal to the whole null space. Okay. But those definitions, I think, are useful enough, right? So any two vector x, y whose dot product is zero is said to be orthogonal to each other. Vector y whose dot product is zero with any x in L, that one is orthogonal to the subspace L. Okay. Now, just a little bit more definitions. The space of all vectors y orthogonal to linear subspace L is called orthogonal complement. Is called orthogonal complement of L and denoted L perp. That is this symbol called perp, perpendicular perp. At least this is how it called in LaTeX. I'm not sure if there is a better way to pronounce it. Yeah. So space of all vectors y orthogonal to linear space L is called orthogonal complement of the space L and denoted as L perp. Okay. Good. And equivalently, the space of all vectors y such that dot product of y and x is zero for all x in L is called orthogonal complement. But those are clearly equivalent. All right. So if x is in L and y is in L perp, this implies dot product of the two equal to zero. Okay. So this is orthogonal vectors, vector orthogonal to a subspace and its orthogonal complement. Three definitions that we saw. Good. Good. And we can see that the idea of a closest element can be used here. Okay. Now, let us see. Oh, by the way, do we have questions here? Sorry, I went through three definitions without asking. Do we have questions here? All right. I will move on, but please stop me as soon as you have questions. So let L be an orthogonal basis, orthonormal basis in the linear subspace L. All right. Take vector A, where x lies in subspace L and y lies in L perp. Okay. So we have this vector, which is x plus y. X lies in L, y lies in L perp. Okay. Definition. We call x a projection of A onto subspace L. And we call y a projection of A onto subspace L perp. if if A is given to X plus Y, and X lies in L and Y lies in L perp, then X is a projection of A onto L, Y is projection of A onto L perp. Notice this wouldn't work for other subspaces. It wouldn't work, for example, if X and Y didn't lie in mutually orthogonal subspaces. If they were lying in some random subspaces which were not mutually orthogonal, then it won't work. This whole idea works exactly because the subspaces are orthogonal. Okay, you can think about why it won't work, why it won't make sense. Well, why it would make sense, but it's very least, if this sounds a little bit kind of like why just a sum of two vectors instantly gives you a projection, like, how is this, the fact that A can be decomposed into X plus Y, how is this giving you a projection? Well, it is because X lies in one subspace and Y lies in its orthogonal complement. Only that is why. You couldn't do it without this orthogonality property. Okay, just to give you direction in your thinking. Okay, now projection is the closest element in the subspace to a given vector. That is, again, this whole idea of using closest elements. Okay. So projection of A can be found as X equals to L pseudoinverse A. We saw it before, right? We saw it before. We saw it before when we were analyzing residuals. So this is where it comes from. I'm not going to give you derivations, but you can see where it comes from analyzing residuals of least squares. One way to derive it. There are, of course, many ways. Okay, since L is orthonormal, we can rewrite it in this way much nicer. X equals to L transposed A. Good. So that is how we can project A onto subspace L. Good. Now let us see what else we can do. Well, first we remember that A is still X plus Y, right? But X is now equal to L pseudoinverse A. We can substitute instead of X, this guy, we can get it here, right? And what we get is this expression 12. From the expression 12, we can find Y, because we just put everything onto the left-hand side. We isolate Y, and we get the expression for Y. And it looks like this. So notice we already saw this expression as well. That's not the first time we saw something like this. What we see here is the same expression we saw when we were analyzing the residuals. Okay. So if this expression looked quite like what we saw when we were talking about how close AX can get to Y, this looks exactly like the residual between Y and AX. And that is not a surprise, of course. There are connections between those things. So it's not a coincidence. Surprise, maybe, yes, not a coincidence. Okay, so this is how we can project onto the orthogonal complement of L. This is how we project onto L. This is how we project onto orthogonal complement of L. All right. And then this pattern will repeat. We'll often have projector. I minus projector is the orthogonal complement. Okay, good. Since L is orthonormal, we can also do it with transpose. So now we saw how to project an element, how to project a vector onto a linear subspace if we know basis in the subspace. We can, if it is orthonormal basis, we can do it this way. If we want to project onto the orthogonal complement, we can do it this way. All right. So that is what we have. Any questions so far? Okay, let me just check how much time we have. Just a moment. We have 5 minutes. We have 5 minutes. Okay. Let me just see what is the next topic. All right, I will quickly go through the row space. I will try to just get it a couple minutes, and then we will finish for today. All right, so if n is a null space of A, then orthogonal complement of n, so this n perp, is called a row space of A. Okay, this is a row space of A, just orthogonal complement of the null space. Row space, you can think of it as a space of smallest norm solutions of Ax equal to y for various y. That is not a very clean way of thinking about it, because you have to now think, is there a one-to-one, between those and so on? So it's not like you have to be precise. This is not precise. Right? This is precise. This definition is precise. This is not precise. You have to be more explicit what you mean. But yeah, it's orthogonal complement. So every vector that is orthogonal to any element in n in null space would automatically be in the row space. Okay. And every vector, period, any x can be decomposed into 2 components: null space component and row space component. And how do we find those 2 components? By projection, the way we discussed in the last slide. Okay, because those 2 spaces are orthogonal, so for them we can easily project. Let's look at those projections. So given vector x, matrix A, and the null space basis n, we can check if x is in the null space of A. Simplest way to check is to just write it as Ax equal to 0. That is the simplest way to check. Sometimes we don't want to compute Ax equals to what it is equal to. Why? Well, for example, if A is a huge matrix and its null space is like 1 or 2 vectors, it may be much faster to do it without this computation. So instead, what we can do is we can find a projection of X onto the orthogonal complement of the null space, which is a row space, right? Why do we need to check? What does the row space have to do with it? We were trying to check if n lies in the null space. If it has a non-zero projection onto the row space, it means it doesn't lie in the null space completely. It sticks out. So it has a component in the null space, component in the row space, right? So it doesn't completely lie in the null space. That's the point, right? So by checking that it has 0 projection into the row space, we check that it lies in the null space, right? And how do we check it? Well, this way. Where did it come from? Remember, to project into the orthogonal complement, you do I minus n, basis transposed. That's how. With the same logic, if we want to check if the vector lies completely in the row space, we do it this way. For the row space, the orthogonal complement is null space. So we need to check that the projection to the null space is 0. So this will be a criteria that the vector lies completely in the row space. All right. Good. So that is what we can do with them. That is of course, let me just say, this is of course a projection onto the row space, or in the null space. This is a projection onto the row space. Okay. I think maybe this is enough for one day. We have a lot to go. You can see we have 17 out of 35 slides. So we have more to see next time. But next time we'll go through the two remaining spaces, projectors and SVD decomposition. If you have questions, if you will have questions, make sure to ask them. You can ask them now. You can ask them before the next lecture. You can ask them in the chat. I will be more than happy to answer. Also, my suggestion for exercise is to try to prove whatever sounds non-convincing to you in the lectures, or try to prove that this is wrong. Right? That is the best exercise. That is it for the content of the lecture. I will stop the recording here.